Hello, I am Seema and welcome to part 20 of the chapter Organic Chemistry, Some Basic Principles and Techniques. In part 19, I told you about the reaction mechanism and I told you how in an organic reaction you have reactants. The reactant of your main focus is known as the substrate and the attacking reagent, how they react with each other result in the formation of an intermediate, and how the intermediate then further reacts in order to, or breaks down in order to give you the products. So what is actually happening in a chemical reaction? Whenever reactants or a chemical change takes place, in the reactants, whatever bonds are present, some of those previous bonds break. And when the previous bonds break, in the products, a rearrangement takes place and new bonds are formed. That is what a chemical reaction is. Now this breaking of previous bonds is known as the fission of a bond. So the topic of this video is the fission of a covalent bond. In organic chemistry, we have compounds of carbon and hydrogen and other elements, of course, which will be present in the molecule, basically carbon compounds. And they are all bound together by covalent bonds, all the carbon atoms. So the breaking up of this covalent bond between two carbons, or carbon and a hydrogen, or carbon and oxygen, or carbon and sulfur, basically the breaking up of the covalent bond, how does it take place? That is what we will understand. So we call the breaking up of bond is known as the fission of a covalent bond. There are two ways how the bond can break. One is known as the heterolytic fission and the other is known as homolytic fission. You understand, you've studied in your lower classes what a heterogeneous substance is, what a homogeneous substance is. Homogeneous substances where all the particles look the same, for example gases. You can't tell which one is which, because they just you can't tell with naked eyes the difference between the molecules. You may be having nitrogen, you may be having carbon dioxide, you may be having different gases, but you can't tell them apart. So a substance that appears to be the same, even if it has got different components, is known as a homogeneous mixture. And a heterogeneous mixture would be one where you can tell the different substances apart. For example, you have sand, the different sizes of the particles will tell them apart. Or you have, let us say, rice mixed with lentils. The shapes are different, the colors are different. You can tell that it's a mixture of two different things. Or oil and water, where they stay apart. So you can tell this is the oil layer and this is the layer of water. So homo means same and hetero means different, basically. When you are talking of it in terms of fission, heterolytic, what is lysis? You've studied about electrolysis. Lysis means breaking down. Fission, lysis, they are all the same. So heterolytic cleavage. Cleavage is again breaking down. Lysis is also cutting apart, breaking down. Hetero means different types. So a cleavage that leads to a difference in the particles that is formed. And what is this difference? The two particles that will be formed as a result of the breaking of this one bond, one of them will be positively charged and the other will be negatively charged. So it results in the formation of opposite charges. They are not the same. That is why it is known as heterolytic cleavage. So let's study about heterolytic cleavage first. In heterolytic cleavage, the shared pair of electrons, what is a covalent bond? A covalent bond is formed between two atoms where both the atoms contribute one electron each, and this is a shared pair of electrons between the two atoms. When heterolytic cleavage takes place, both the electrons, if it was just a normal breaking of the bond, I contributed one electron and my neighbor contributed one electron. That is, that electron, let us say, is our arms. My arm is one electron, his arm or her arm is another electron. We hold hands, we form a bond. That's a friendship. Okay, if this friendship has to break, I take back my arm, she takes back her arm, and the friendship breaks. Cleavage has occurred. But if, let us say, that friend of mine was stronger and the breaking of the bond was taking place. And what she did, she pulled away my arm. Now she has two arms, her own and mine, and I am left with one arm less. So I am deficient in an arm while she has got an extra arm. Since the arm is an electron which is negatively charged, she gets an extra negative charge, and I have lost one negative charge, so I become positively charged. Because the number of positives and negatives were equal in me. When I lost one negative, that one positive which was balancing it will now make it positive. So that is what happens. In a heterolytic cleavage, the shared pair of electrons, this pair, one contributed by the other atom and one contributed by me, this shared pair of electrons remains with one fragment. Whenever you break a thing, what you get is other fragments, the broken parts. So both the electrons remain with one fragment, that is my friend, and after heterolysis, one carbon has a sextet. You know, why did carbon form the bond? In order to complete its octet. So when these two electrons are contributing towards the completing of the octet of the carbons, let us assume that all other valencies are fulfilled. So there should be 8 electrons in the outermost shell, or there should be 8 to complete the octet. So each atom had 6 electrons. I had 6, my friend had 6, and these 2 electrons are being shared to make them 8. So 6 plus 1 was 7. My friend also had 6 plus 1, 7. But these 2 are shared, so these 2 are forming the 8 electrons. 6 plus 2, 6 plus 2. So when this bond breaks in a heterolytic cleavage, after heterolysis, this carbon is left with only a sextet of electrons. I will be left with only 6 electrons because my 7th electron has been taken away by the friend in the cleavage. So it has a sextet of electrons, and the other, that friend of mine, she's not good, believe me. She has all the 8 electrons, so she has an octet, and I'm left with just a sextet. So I'm at loss. So the other one has an octet with at least one lone pair of electrons. This octet that is formed, it has at least one lone pair of electrons. Why? Because this electron that it took is not in a bond. Therefore, its own electron and this electron that I gave, this arm that I gave, is a dangling lone pair of electron. So it has an octet, its octet is complete, but one of those electrons is just dangling one pair, and that will be a lone pair of electrons. And it would have a negative charge. You understand why would it have a negative charge? Because I had 7 negatives, she had 7 negatives, she took away one of mine, I'm left with 6 negatives, therefore 1 positive, and she has 1 negative, that extra negative that she took away. Take a look here. You have methyl bromide or bromomethane. When heterolytic cleavage takes place in the case of bromomethane, the bond between carbon and bromine breaks. And since bromine is more electronegative in comparison to carbon, it has a tendency to pull the electrons towards itself. So bromine is that friend of mine, took away the pair of electrons to itself. And therefore bromine became negatively charged. And poor methyl group is left with only 6 electrons, a sextet of electrons, and a positive charge. Therefore, this forms a cation. Anything that's positively charged is known as a cation, and any species that is negatively charged is known as an anion. So this methyl is forming a cation, it's the methyl cation, and the bromide is an anion. So due to heterolytic cleavage, you get 2 ions, a positively charged ion and a negatively charged ion. And since we are studying organic chemistry, when you have these cations which have carbon atoms or alkyl groups, they are cations of carbon. Therefore, they are known as carbocations, cations of carbon. So such reactions where the bond is breaking in a heterolytic manner are known as ionic reactions, because it is resulting in ionic formation of ions, or hetero reactions or heterolytic reactions, or they are known as polar reactions. So we understood that as a result of heterolytic cleavage, a cation is formed which is known as the carbocation, because it has carbon which has the positive charge, therefore they are known as carbocations, and an anion is formed. Now this is a case where the other atom which was attached was more electronegative, therefore it had a tendency to pull the electron, shared pair of electrons, towards itself, making the carbon positive. The opposite could also happen, where you have an atom which is even lesser electronegative than carbon, and instead of pulling the shared pair of electrons towards itself, it actually donates the shared pair of electrons towards carbon. In that case, you will get an anion with negative, where carbon will have a negative charge, and that would be known as a carbanion, just as we are calling it a carbocation here or carbocation here. We'll come to that later. Let us first understand this. So carbocation is formed and an anion is formed. And one example is this methyl carbocation, which was formed in this reaction. It is also, previously it was known as the carbonium ion, but we still call it the methyl carbonium ion. And we also call it the carbocation. Now carbocations can be classified into primary, secondary and tertiary carbocation. So when you did nomenclature, you already know what a primary compound is, secondary or tertiary is. Yet, let me just revise it here or repeat it here for you. The carbocation has a carbon which has a positive charge, right? That carbon is the alpha carbon, or the carbon at which the positive charge is present. If this alpha carbon is attached to either no other carbon or just one other carbon, then it is a primary carbocation, or it is a primary alpha carbon. So here you see in methyl, this carbon has positive charge and it is attached to 3 other hydrogens, but there are no 2 carbons attached. There is actually no other carbon attached to it, only hydrogens. So it is a primary carbocation. In CH3, CH2 positive, where this carbon has the positive charge, this is the alpha carbon and it is attached to one more carbon atom. So whenever you have the alpha carbon attached to one more carbon atom, it is a primary compound. So this is also a primary carbocation. So what carbocation would it be? It would be, this is the methyl carbocation, this would be the ethyl carbocation. This one on the other hand has a carbon, the alpha carbon, and to the alpha carbon 2 CH3 groups are attached. So this carbon, alpha carbon, is attached to 2 other carbon atoms. Whenever the alpha carbon is attached to 2 other carbon atoms, the compound is known as a secondary compound. In primary, it is attached to only one other carbon atom or no carbon atom. Then that is a primary. But if it is attached to 2 carbon atoms, it's called a secondary. So this is a secondary carbocation. So this would be a secondary propyl cation. Why propyl? Because in all there are 3 carbons, right? And this one, what is this? This has got a carbon, the positively charged carbon, and the positively charged carbon is attached to 3 other methyl groups. That is, it is attached to 3 other carbon atoms. If it is attached to 3 other carbon atoms, it means it is tertiary. Any alpha carbon that is attached to 3 other carbon atoms would be a tertiary alpha carbon. So this carbocation would be a tertiary carbocation. So carbocations can be classified into primary, secondary and tertiary carbocations. The methyl here, what do we see? That as the number of methyl groups attached to the alpha carbon or the carbon bearing the positive charge keeps on increasing, the more stable the carbocation is. What is the importance of its stability? Why do we care about its stability? Any ion or any product of a reaction that is stable would be formed easily. The more stable the product is, the more are the chances of formation of that product. If the product that is formed is not stable, why would it form? Why do you study? So that you get educated And that provides a kind of a stability in your life in the form of your profession, in the form of your affluence or whatever. So unless and until the greater the stability, the more are the chances of the formation of that ion. And what do we see? That the carbocations, if we classify them, they could be primary, they could be secondary, they could be tertiary. But what is the difference between primary, secondary, tertiary? Is the number of methyl groups or carbon atoms attached to the alpha carbon. So the larger the number of carbon atoms attached to the alpha carbon, the more stable is the carbocation. Which means that primary is the least stable, secondary is more stable, and tertiary is the most stable. Out of these two primary, this one is more stable. Why? Because here one carbon is attached, and in methyl there is no carbon attached to the alpha carbon. Therefore, this is the least stable, this is more stable, this is even more stable because it has 2 methyl groups attached to the carbon, and this is the most stable, which has 3 methyl groups attached to the alpha carbon. How do you explain this? Why is a tertiary carbocation more stable? Why is a secondary carbocation less stable than that and lesser? This stability of the carbocations can be explained on the basis of inductive effect and hyperconjugation effect, both of which you have not yet studied, and I'll be doing them in the consecutive videos. But let me just give you a minor, a little hint. Methyl groups have a tendency to pull electrons towards themselves. So it is the same thing, my friend who was stronger than me pulled the electron away and made me positively charged. And I don't have just one dishonest friend, I have many more others, I have another one here, is also a carbon atom, and that also has a tendency to pull the electrons towards itself. So that is pulling the electron of that bond that I'm forming with it also towards itself. The friendship is not broken, no fission occurred, but it has a tendency to pull the electrons. So I was already positively charged. On top of it, this is also pulling away my other arm. So I'm going to lose even more electrons and become even more, the positive charge becomes more pronounced. And the negative charge is moving away from me. So inductive effect is where you have a group which has a tendency to pull the electrons towards itself, thereby making the positive charge stronger. And the stronger, any ion that has a stronger charge, its formation would be quicker, or it would be more stable. Since it's a positive charge, the more the positive charge is, the greater are the chances of its formation, because an ion never stays in the ionic state. If it is more stable, then it would, stability in terms of not that it is going to stay like that forever. It would have a greater tendency to form the product. So inductive effect and hyperconjugation effect is also kind of somewhat similar, but in which you have a bond between carbon and hydrogen in the methyl group, and there is an empty bond in this group. You see, the octet is not completed. So that empty orbital and the sigma bond, they overlap with each other, and a kind of a falls, those electrons start moving in the empty orbital of the alpha carbon, thus again making it more stable. So both greater the number of carbon atoms or methyl groups, greater is the inductive effect, greater is the hyperconjugation effect. And the more the inductive effect and hyperconjugation effect, the better is the carbocation, or more stable, or more chances of its formation. And once it is formed, its formation, once it is formed, a cation is an ion, and the next step would be an ionic reaction, which would be much faster. So the formation of a tertiary carbocation is the easiest, or it would be facilitated the most, because of the presence of these methyl groups, and due to greater inductive effect and hyperconjugation effect of the methyl groups. We'll come to it again when we do these videos on both inductive effect and hyperconjugation. Now this carbon, which bears the positive charge, carbon, should form 4 bonds if it is sp3 hybridized, like you have in methane. The 4 bonds, they should be sp3 hybridized, and you have 1, 2, 3, and 4. Let us assume that this is the methane molecule, right? 4 bonds, 4 of them along the 4 corners of a regular tetrahedron. In any direction you have the same shape. If one of these is removed, that friend who took away the electron and went away, not only went away, took the electron away also. Now these 3 bonds will form a planar structure, because if they remain like this, there will be more repulsion. But if they acquire maximum distance from each other to form a triangle, now there is minimum repulsion, 120 degrees between each bond. But that orbital, that electron went, but the orbital, empty orbital is still there. That empty orbital forms a perpendicular on this. So the empty orbital, let us say this one, is perpendicular to the plane of the triangle. It becomes perpendicular to it. So such an arrangement with an empty p orbital and 3 sigma orbitals is known as this. These 3 will hybridize with one s and 2 p orbitals, and the empty p orbital will be perpendicular to it, and the molecule will be triangular in shape. That is what happens in the case of a carbocation. The carbon which has the positive charge is sp2 hybridized. Therefore, it will form a triangular planar structure. So if you have CH3, the 3 hydrogens are along the 3 corners and there is one empty p orbital. If you have CH3 whole twice CH, 1 hydrogen is here and 2 of these are methyl groups and there is an empty orbital here, p orbital. If you have CH3 whole thrice C, then the carbon in the center, and all 3 of these are methyl groups and there is an empty p orbital perpendicular to the plane of this triangle. Right? One lobe of the p orbital above and one lobe below it. So that is what you see here. It is an sp2H bond. In CH3, you have 3 sp2 hybridized carbons and hydrogen bonds. All these are sp3 hybridized orbitals forming a triangle, and this one is, if this is the triangle, this is perpendicular to it. This bond that you see is an empty p orbital perpendicular to it. So that is the structure of a carbocation. Let us move ahead now. If carbon in heterolytic cleavage, okay, this was where carbocation is formed. Let us now come to the other part. Heterolytic cleavage took place, but this time it's not the friend who is stronger. This time it's me who is stronger. That one is electropositive. So instead of pulling the electrons, my friend pulling the electrons away from me, this time it's me. I will pull the shared pair of electrons towards myself when the cleavage occurs. So now I have 2 arms, right? An extra arm. So I become negatively charged. If carbon in the heterolytic cleavage gets the electron pair, we get the carb anion instead of carbocation, which was carbocation is formed by loss of electrons. So this is a poor thing, you know, it has lost the electrons. But carbanion is the stronger one. It got the electrons towards itself. So heterolytic cleavage took place, both the electrons went to the methyl group and it formed a carbanion. Just like carbocations, carbanions would also have the negative charge on the carbon. That is why they are known as carbanions. And just like carbocations, which are all ions, are unstable. Therefore, whether a carbocation is formed or a carbanion is formed, ions cannot exist as ions in nature. They would always combine and form a neutral compound, an ionic compound. But they will always balance charges. So, whatever ion is formed, whether it is carbocation or carbanion, or carbanion, they are unstable and they are reactive species. They would react in an ionic reaction and form a stable compound. So this was heterolytic cleavage. Let us now come to the second type of cleavage. The first was heterolytic, where the cleavage took place with an imbalance. What was the imbalance? Both electrons went to one atom. So you either got a carbocation or you got a carbanion. The other type is a more balanced kind of cleavage. Both of us are very friendly, me and my friend. We decide simply to just break our friendship because I'm going away to another town and she's going away to another town, and there's no chance. It is an age where you do not have internet, so cannot text to each other, and the mail doesn't work, whatever is the reason. She's going to Mars. So she's going to stay on Mars and there is no communication. So now we have to break our friendship. But both of us decide that, okay, I get my electron back, you take your electron back, and you go as you, I go as me. Complete. 7 electrons, I have 7 electrons, my friend has. Both of us do not have a completed octet. And that situation also is not very good. Not having a completed octet means that I will have to react in order to complete my octet. But since my friend went away to Mars, I'll find other friends, and I'll make a bond with them. So such a cleavage where the bond breaks and both the species take their own electron away, and there is no heterolytic, it is homolytic. The bond is breaking, the bond was formed when both of them contributed 1 electron each, and when the bond breaks, both of them get that electron back. So in homolytic cleavage, the breaking of the bond takes place where both the atoms get their electrons. This is represented, do you see in heterolytic cleavage what did we do? We made an arrow, a curved arrow, showing the movement of electrons. That in formation of carbanion, the pair of electrons is moving towards methyl group. In the formation of carbocation, we found that the shared pair of electrons were moving towards bromine. In this case, what we do, we show 2 arrows, and 2 of them are half arrows, half curved arrows. They are like a fish hook, like you've seen fishermen or who try to catch fish with the help of a hook. So that is a curved hook. So therefore, these are known as fish hook arrows. So arrows like fish hooks, single hooks. The single hooks mean that a single electron is going to each side. 1 electron of this bond, of this covalent bond, 1 electron goes to the methyl group and the other electron goes to the other atom, whatever the other atom is. And therefore, whenever an atom has a single electron like this, which is not bound, it is known as a free radical. So you get free radicals, both the alkyl group and the other species, you get free radicals of them. By homolytic cleavage, we get free radicals. Free radicals are not charged. They are not charged species, but their octet is not complete. So therefore, they are not satisfied species either. They are not stable. They badly need that 1 electron to complete their octet. So they will react, but they are not ionic in nature. They are neutral species. Remember the difference between a free radical and an ion. In homolytic cleavage, the cleavage takes place evenly. Both atoms get their electrons, and it results in the formation of very reactive species known as free radicals. But the free radicals are not ionic. They are not charged. They are neutral species. Just as we had the cations and anions, you have alkyl free radicals could also be primary, secondary, tertiary. And their stability also increases in the same way. That is, the tertiary butyl free radical is more stable than the primary one. So just as we had studied in the case of carbocations, you have methyl free radical, you have ethyl free radical, you have isopropyl free radical, and you have tertiary butyl. Do you see the alpha carbon here? This is the carbon which has a single electron, so it is the alpha carbon. Here this is the carbon having a single electron, this is a carbon having a single electron, and this is a carbon having a single electron. So all of these, the stability would still be in the same sequence. Organic reactions that proceed by homolytic fission. Organic reactions in which homolytic fission takes place. What is formed? Free radicals. Therefore, such reactions are known as free radical reactions. Just as when you had heterolytic cleavage, these reactions, whether carbocation was formed or carbanion was formed, they were called ionic reactions or heterolytic reactions or polar reactions. These are known as, on the other hand, they are known as the homolytic fission or homolytic fission reactions or free radical or polar reactions. And since there are no poles, homopolar means that there is no pole. Pole means positive charge and negative charge. Since there are no poles, therefore we also call them non-polar reactions. That there are no charged particles formed here. So this was the fission of a covalent bond. And with this, I'll wrap up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.